Okay, last group's lesson, last further maths lesson of year 12, in fact, so I'm sure you're all very excited about that. The last thing we have to do on groups, abstract groups. So it's not really kind of anything specifically that's new, but it's all of the stuff you already know about. So subgroups, isomorphisms, orders of groups, properties of groups, but just in more general terms. So we're not going to have necessarily a finite group. We're not going to have a group where we necessarily know all the group rules. We're going to have a group that we don't really know much about, that's abstract. What it means, of course, I don't like them particularly much because, you know, I just love thinking of symmetry groups all the time, and these abstract groups are just by definition trickier to get a handle on. So we're not really looking at anything specifically new, although there is one property and one little proof, little result that you need to be able to show yourself. But we're essentially going to go through types of questions you may be asked. One thing that is actually classed in the groups, in the abstract groups, are questions like, I haven't got one lying around, but questions where you've got all of the group properties in terms of, normally it's A's and B's, isn't it? So you might have something like, okay, you've got a group that consists of powers of A and B such that A squared is equal to B cubed is equal to E, and A squared B is equal to BA. So those kind of groups are in fact counted as abstract groups. However, they're quite nice because you always are able to determine exactly how many are in there. So that's still classed as abstract groups, but they're definitely on the nicer end of abstract groups. Anyway, this question here, this example here, we have got an operation star on a set. So of course it's not committing yet to it being a group or not. What we need to do in this question is show whether it's a group or not a group. So we've got all of the integers apart from plus or minus 1. Okay, so it might transpire through, and what we do, we see why that is the case. And what we've got, this star, it kind of looks like a product, doesn't it? But actually what's going on is that you're adding A plus B, and then it's over 1 plus AB underneath. So determine the identity element. Now, because these are kind of abstract groups, because everything is expressed in kind of technical language, I would answer in a more technical way as well. So you might be able to kind of just look and spot. And I think if it was worth 1 mark, I would say that, okay, it's possible to do this by inspection, but you know, I deliberately have taken the marks off and I can't even remember what it was. So I'm going to do this in the more formal way that I would definitely encourage you to practice. So determine the identity. Right, so the identity. So we need the identity element, which we generally call E, such that A, I'm going to call it star, asterisk, you've just got too many syllables, together with E is equal to A. And of course it also means, you know, the strict definition has got it the other way around as well. But what I'm going to do, I'm going to start with that, find my identity, and then I'll just be able to show that afterwards. So what we are looking for then, we are looking for, so really in place of B, I'm going to be putting this mystery element E. You could of course leave the B's in there and rearrange for kind of B, but I just want to make it obvious all the time. Right, I'm looking for the identity, so I've put that E in there. And we want that to, so there's my A star E, I want that to equal A. And then it's just an algebraic equation that you can rearrange. That's going to be A multiplied by 1 plus AE. I can expand that bracket just as I normally would. A plus E is equal to A plus A squared E. The A goes, and I mean, just be careful about in dividing through. You might think, oh, there's kind of in it, but let's do this kind of properly. You know that dividing through by factors is always a little bit dangerous. So let's factorise that. So we either have A squared equaling 1, which would mean that A was plus or minus 1. However, we're not allowed that just by definition in our group. So what I've got there, I'm left with the only other option. So, but we can't have that, so that was not allowed. Or E is equal to 0. And is that in our set? Yeah, that's in our set, so we're allowed that. So our identity is equal to 0 as 0 is contained in our set S. I just checked this the other way around. It says determine, it doesn't really say prove, but of course if you did that the other way, if you did naught with this, sorry, if you use 0 star B, you would again just get B, wouldn't you? So you can see, put 0 in place of A, it just becomes B over 1. So that works. So there is my identity. Right, so next, for each element of A in the set, describe the inverse. So by describe, it doesn't mean, oh, it's just the thing that gets you back to what you said. That's not it. It doesn't mean describe in words, of course. It's mathematically describe. So again, I'm going to do it in kind of a more formal way, depending on the wording in the question, depending on the marks. You could do it the technical way. Some of you, I'm sure, are just looking at that and able to just see, oh, well, it's this, isn't it? But the way you would prove it is to say, right, I need an element A inverse such that A, and I've written it there without the star, A star A inverse is equal to E. So you put A and A inverse into that equation there. So we've got A together with A inverse over 1 plus A inverse. We want that to equal E. And E, in fact, we've worked out is 0. So let's just put that 0 in there. We know, just by definition, A inverse is always going to be equal to the identity. And so that is, in fact, equal to 0. So then we're just left with A plus A inverse equaling 0. A inverse is negative A. So our inverse is negative A. We need to check, do we have closure there? We have closure there because we are allowed any integers apart from plus or minus 1. So that is certainly in our set. So that is our inverse. Okay, now the associativity. What you are hoping for in your exam question is a nice little phrase like associativity assumed. That is certainly what happens quite often, unless it's particularly straightforward, or unless, I guess, they're short of marks, unless this is the last question on the paper. So if it's associative, excuse me, we need 3 elements. We need 3 elements because we need to be able to show that A star B star C is the same as A starred with the result of B star C. So that's what we've got to prove. So I'm going to work out this one first. A star B starred with C. I've got my expression for A star B there. And I want to work out what that is starred with C. So it's going to look horrible, but we just need to get stuck in. So it's the sum of the two on the numerator, so a plus b over 1 plus ab, over 1 plus the product of the two underneath. So a plus b over 1 plus ab multiplied by c. So we have to simplify that. Say we have to simplify that. What, of course, we have to show is that this one here is going to be the same as that one. But, of course, what I'm going to have there is lots of B and C brackets. So I think it would be very much worth my while just to get rid of those double fractions. So, of course, we do that by multiplying by 1 plus AB over 1 plus AB. That is going to leave me with just an A plus a B term there, and then here I'm going to have a C times by A plus B, and then underneath I'll have a 1 times by, sorry, a 1 times by that, so that'll be 1 plus AB. And then here, that denominator will go with that, so I'd just be left with an A plus B multiplied by C. So that looks like it might be something, once I expand the brackets, that will work for me. I'll have an A plus B, that will get me a C. And I've got an ABC. And underneath, I've got an AB and an AC and a BC together with a 1. And I'm liking the look of that because, of course, what we've got is we've got symmetry. So I've got the sum A, B and C and then product A, B, C, and I've got this kind of two-way thing going on there and then the 1. So I'm thinking that this is going to work. So let's do the other one. So I've got my A starred with B star C. So I'm going to just kind of plonk the A there and write down that result, but with B's and C's in. So I'm going to have the sum on the top and 1 plus the product on the bottom. Now, doing that with that, I have the sum on the top. So that's going to be A together with the whole of that. And then I've got 1 plus the product on the bottom. So 1 plus A multiplied the whole of that. Again, I'm going to do that nice little thing with the denominator, so that will make A lots of 1 plus BC plus B plus C. And on the denominator, I will have 1 multiplied by 1 plus BC plus that one will go, so it'll be A, B plus C. Expand the numerator, I'll have an A plus a B plus a C, plus that product there, the ABC. And then underneath, I've got my 1 and then BC plus AB plus C plus AC. So again, I've got exactly the same there, so I can conclude that that is equal to A star B starred with C. Hence the operation star is associative. Okay, wonderful. So back to the question. A, B and C determine whether it forms a group. So, of course, it's taken us in a particular way here. We know there are 4 properties that we need to state, we need to show. Identity, inverse, associativity, of course, closure. And quite often, I think, when you are finding these yourself, you often tend to do closure first. The list, certainly when we write down the definition, is closure, identity, inverse, associativity at the end. So it's taken us down this particular route. I wonder why. If we look at D, determine whether it forms a group. We've got integers and we've got division there, haven't we? A division, that line there. We've been looking at fractions the whole way, haven't we? And we know that there's a problem when we come to looking at the division of integers. If I take two integers there, I don't know, 2 and 3. I'll have 5 on the top and I'll have 7 on the bottom. 5 over 7, that isn't an integer. So remember, to prove that something's a group, we have to show all of those things. To prove that something isn't a group, we are just essentially looking for a counterexample. We can see that the set S under star is not closed. Of course, that wouldn't be enough. You have to show a specific example. So as I said, if we do 2 with 3, that's going to be 2 plus 3 on the bottom over 1 plus 2 times 3. 5/7. That still wouldn't be enough. Okay, so we have to spell it out. We have to spell it out and say, but 5/7 is not in the integers, so it is not contained in our set S. Hence, S under star is not a group. If the question had have said, forgotten all of that and just said, is it a group? Of course, you could have just gone straight for the closure. Hopefully you'd have spotted, okay, yeah, we're not allowed because we're going to have some fractional values. You could have gone straight there. However, the way the question's taking you through, of course, it's wanting to test your knowledge of group properties and then that final thing at the end. Okay, all right, so one example then. Next up, as I said, there is this one specific property that you may be asked about. It's called the inverse property. And there is something similar with matrices. So I think matrices, it's pure core 1. And that is if you have two matrices and are looking for the inverse of the product, it's actually kind of the reverse thing like that. You do the inverse of B and then the inverse of A. Apply them in that order. So, of course, it's a comparable thing. And this is sometimes, I think even in our textbook, it's known as sometimes the socks and the shoes property. I don't know how this is supposed to help, really. But socks are A and shoes are B. You put your socks on and then your shoes on in that order. So the inverse of that, you of course have to take your shoes off first before you take socks off. Okay, so yeah, it's kind of obvious, but people like to talk about the socks and shoes. You see them in some textbooks. However, you just need to be able to prove it. Essentially, you have to remember to start with a specific thing. So, don't start with that statement there and somehow trying to get to one for the other. You want something concrete to start with. And that the element AB, so that element there has an inverse of AB inverse. Okay, so I know we've got to show that that is equal to that, but I'm just thinking about the element AB and the element inverse of AB. So that means that I definitely know that AB together with AB inverse is equal to the identity. Now, this will be a proof. Because it is a proof, you need to make sure that you've got all the steps. And I'm sure some of you are thinking, she's talking to me here, she's talking to me here. Yes, I'm talking to you. Make sure your proof has got all of the elements. Some of these elements are obvious. The exam question will probably say, prove this, stating at each stage which group property you are using. So they really spell it out. So what I want to try and do is to change this statement into this statement here. So you can imagine we go through all the stuff and at the very end we want to get to AB inverse equals B inverse A inverse. So what we have to do is to get rid of these two elements here. So what I'm going to do, and I'm stating what I'm doing because I'm proving it, I'm pre-multiplying by A. Again, this is language that we use when we do matrices, don't we? When we do matrices, we pre-multiply, we post-multiply. So I'm going to have AB together with my AB inverse and my E over here. I'm going to pre-multiply by A, so there's the A, and there's the A. Now what I am going to do, sorry, I'm not going to pre-multiply by A. That doesn't get me what I need. I'm going to pre-multiply by A inverse. Okay. Now what I'm going to do, I'm going to use the associative property. So I am going to change the order of these brackets here. So I haven't done anything yet to the right-hand side. But by doing that, I can, of course, say that that is equal to E. I used a particular property there. I need to write it down because this is a proof. I don't think I'm going to have enough room. By associative, I think I might have missed something out there. By associative property is what I've done there. So that is equal to E, B, AB minus 1. Again, I've used something there. Let's write it down. So as A inverse times A is equal to E. Now what I want to do is get rid of that B. I get rid of that B by pre-multiplying by B inverse. So now I have got B inverse B, AB inverse, and now I can put a B inverse next to that A inverse there. I've had that E throughout. That, of course, kind of isn't needed. I'm going to forget about that now. And here, I've just got that product. So I can just say that that is equal to E. However, I only get the credit if I write it down. You'd have been asked to write down all your group properties. So that's the last group property I've used, which then leads to this. Okay, 3, possibly 4 marks. A stumbling block for many people is kind of realising that they have to start there. Although actually saying that, you could do all these steps in reverse, couldn't you? You could start with that, pre-multiply both sides by B, pre-multiply both sides by A. But I think it's, certainly much, much nicer, mathematically nicer, isn't it, if you kind of start with a property that you already know. Starting with the thing you've got to prove and working backwards are always, a little bit odd. So start with the thing that you know, keep working. Yeah, they're all algebra rules that we know about getting to that final result. Okay, so please learn, make sure you can do that. Okay, so the last question, a little bit more abstract even. In that first one, I know it was quite technical, but there was a set group operation that we could do things with. Even that last one, well, I guess it's because I know what to do. You start with the specific things and there's a set process that you have to go through. This one, a little bit more awkward. So we have got a group, it's got an element A and it's got order N. You could well imagine actually them not actually putting that in there. It is given that X is any element of G distinct from A and E. Okay, so X just isn't getting involved in this kind of power relationship there, so it's a completely distinct element. Proves that the order of this particular element, X inverse AX, is N. Oh, again, look at that phrase. Making it clear which group property is used at each stage of your proof. And then we've got to do something about inverses, and then we're asked about some commutative thing. So we're looking at quite an abstract thing. We're looking at group properties. I'm not even given, I suppose that's a bit of a group rule, isn't it? Okay, but let's think about what it's asking us for the first part. Prove that the order of x inverse ax is equal to n. So what we need to prove, so we need to prove that if I raise that to the power of n, we get the answer of e. So that's the key thing there. So I need to find an expression for that. Let's write it out. X inverse ax, x inverse ax, x inverse ax. Okay, I'm getting a bit bored. We do, of course, have expressions for a product. It's kind of a big pi, isn't it? So similar to the big sigma symbol for a sum, a big pi is a symbol for a product. But what we want to be able to do is to kind of show each of these so we can then take combinations in a different way. So you might think, okay, well, this isn't very mathematical. However, this is the only thing we've got, really. And if you look in exam mark schemes, I'm afraid kind of that's what they do as well. They just say n times next to it. Now, I can see that every now and then, oh, we've got an x combination with an x inverse. I've got an x combination of an x inverse. Of course, here, that last element there will be an x, and that will combine with my x inverse. So what I want to be able to do is to change the positioning of those brackets. So x inverse a, x, x inverse a, x, x inverse a, x, x inverse a, and so on, and then there'll be an x, x inverse ax. And what I am doing there is I am using the associativity of groups. We were told it was a group, so we know that the associative property holds. Okay, so what we're going to have there, we had n lots of everything. I've got an x inverse and an x at the end. So I'm going to have n minus 1 lots of these products here. Okay, so each one of those is equal to e. And I'm going to have my x inverse a at the start, and then I've got an e, and then I've got an a with an e, an a with an e, an a, an e, an a, and then I've got my x at the end. So what I'll actually have here, if I think about my EAs, 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 I'll have n minus 1. Lots of those. So that will be n minus 1 times. So all of those a's and those e's, you'll just have a to the power of n minus 1. All of these, of course, won't do anything. We'll have that a there at the start. So I've got that initial x inverse, I've got that a, and then I'll have an a to the n minus 1. I'll have an x at the end. That now makes x inverse a to the n x. What I'm trying to prove that it's equal to e. We probably should have said here, we needed to write down all our group rules, didn't we? So by associative property, what we've said here is we've used the inverse property because x inverse is equal to e. What I'm about to use here is a to the n was equal to e, so that was our kind of group operation property. So that leaves me with x inverse x, which is equal to e, and again we're using inverse property there. So hence the order of that element x inverse ax is equal to n. Now, it's probably worth an extra little comment, and I bet there'll be one in a mark scheme for this. We have shown that that to the power of n is equal to e. But that doesn't necessarily mean it's the order, because there could have been a power less than n that also gives that property. So we could have half n. We could have randomly 4. Okay, so maybe the order was equal to 4. However, when we do this, we're of course only getting that property because of this key thing here, that a to the power of n is equal to e. You're not going to have that appearing for any power lower than n, so that is probably worth a comment. So we'd say something like there will be no smaller power, sounds better, than n to give a to the power of k equals e. As we were told in here, a is the element that's got order n. Okay, so just remember that just because the power is e, just because that particular power gives you e, doesn't mean that that's the order. There could be a smaller value that gives you that. So that would just be a 1 mark throwaway at the end, but just be aware. Okay, a second one. Express the inverse of that element in terms of these individual elements showing sufficient working. Okay, so the idea is similar to that inverse property that we've just shown. So what I'm going to do here is I'm going to just make up an inverse. I want a bit of notation to be the inverse element, so I'm going to let b be our inverse element. And if you think about what we started with on this proof, we started with the statement how the element together with its inverse made the identity. So I'm going to do the same thing here. The element really isn't very nice. It's that, so we need to find a b such that our element, which is x inverse ax, together with b is equal to the identity, which is e. So what we do is we want to reduce, we want to get rid of all of these things, just leaving me with a b on the left-hand side. So it's very similar to the proof that we've just done. We need to do a bunch of pre-multiplying to get what we need. Showing sufficient working to justify your answer. So even though some of you might be able to see it, please write down each step. So that's the first step. Then what we do is we use the associative property. By associativity. And then that is AXB equaling X. What I've done there is I've used the inverse property. Now I'm going to pre-multiply by, need to get rid of A, so we pre-multiply by A inverse. So A inverse AXB is equal to A inverse X. Again, what I'm going to do here is use associativity together with A inverse A being equal to E. So I'm left with XB equaling A inverse X. And then finally we are pre-multiplying by X inverse. X inverse XB is equal to X inverse A inverse X. Associativity together with X inverse x being equal to E leaves me with B equals x inverse A inverse x. So the inverse of my element x inverse A x is x inverse A inverse x. Okay, so the very last bit. Commutativity, we haven't really... I need some more paper. Sorry, just going over here. Commutativity. It is now given that that's element A, that A commutes with every element of G. Prove that A inverse also commutes with every element. Okay, so again, think about what this means. Think about, something that you can write. You want to write down an equation rather than thinking of this in abstract terms. So think how we started this. We wrote down a specific equation and then we manipulated it. So what this is telling me is that if A commutes with all those elements in G, I know specifically, so it's talking about this other element being, oh no, that was the previous question, wasn't it? Another element being X. Oh no, here, X. Then that means that AX is equal to XA. Commutativity means that, we just switch them around. So that is something that we can work on. Here I definitely know an equation that connects A and X. I want something that involves an A inverse. So because we know how to do that, how to get something in there is that we pre-multiply that statement, which I know to be correct, by A inverse. What that does, it removes the A from there, but it's going to put an A inverse over there. So A inverse AX is equal to A inverse XA. It doesn't say show sufficient work and justify. It doesn't say which is used at each stage of the proof, but it has said prove. So I am going to, state I'm just about to use the A inverse A being equal to E property. So I get that X is equal to A inverse XA. Now think about what I need. I need to show commutativity with an A inverse, so I essentially want this equivalent statement but with A minus 1s there. I've got an A minus 1 with an X there. I need to work out how to get rid of that A there, and of course I do that by post multiplying. So first post multiplying of the day, but you're excited, by A inverse. So X A inverse is equal to A inverse X A inverse. Again, we've got that same property there, A inverse being equal to E. So we have X A inverse equaling A inverse X. There we go, but of course let's spell it out please, which is the commutative property for A inverse. I'm going to tie it up, it's a proof, hence A inverse commutes. Think about how the question said, prove that A inverse also commutes with every element, so hence A inverse commutes with every element of G. So tie it up. Just make sure you answer the question or you give your final statement in terms of what was stated there. Okay, so that's it really for the new stuff. It's just a matter of practicing, getting used to this. I'm sure, next kind of Easter time when we're into the revision process, we will kind of, find particularly obscure questions to have a play with. But it really is the hardest bit of groups. Exam questions either, give you a big 10 marker when you've got a nice group table or you have to draw a table. There are 8 elements there. You've got to pick things out. They're wonderful if you get one of those. But, you know, every year you're going to get a question, you know, more like that. So you need to be careful, and you need to, you know, make sure that you practice these technical ones as well. Okay, so two questions. We've first of all got both taken from 3C, so these are ones to do now. This is taken from an exam question. It says you've got a group, it is given that QP squared, okay, QP squared what? I've checked at the original exam question, it should be Q is not equal to P squared. So these two questions here, I think, because it was a relatively short lesson, oh, I'm on 40 minutes, so maybe not. So I might go through these in a separate little video, possibly. But I've put in solutions and then also solutions for the solutions from the back of the book, and these are the solutions from the exam paper, so you can just kind of look, they're possibly a bit more detailed. But I think I will talk through these as well in a separate video, so you might just want to pause, have a go at these, and then look at the video if you're not sure. Homework, it's going to be fairly lengthy homework, but it's kind of doubling a little bit as work over the summer as well. So I'm aware last week you just had one little groups question at the tagged on to the end of some FLT stuff. So there's going to be quite a lot more. There'll be work solutions as well. So I will post those up pretty quickly for you. Okay, thank you. See you in September.